Welcome to this problem walkthrough. Today, we'll be exploring problem number 1746, titled Maximum Subarray Sum After One Operation. We'll discuss the problem requirements, analyze different approaches, and break down the solution step by step. Let's dive in and start solving. In this problem, we are tasked with maximizing the sum of a subarray in an integer array nums. However, there's an additional twist: we are allowed to modify the array by performing exactly one operation. This operation lets us choose any index I in the array and replace the value at that index, nums I, with its square, nums I, caret 2. After performing this operation, we need to determine the maximum possible sum of any subarray in the resulting array. Remember, a subarray is simply a contiguous part of the array. The input constraints specify that the array nums can have up to 100,000 elements, and each element lies between -10,000 and 10,000. Our output should be a single integer representing the largest subarray sum achievable after applying this operation. Let's look at an example to better understand the problem. Suppose the input array is nums equals 2, -1, -4, -3. Here, we can choose the element at index 2, which is -4, and replace it with its square, -4, caret 2 equals 16. This transforms the array into 2, -1, 16, -3. The next step is to find the maximum subarray sum in this updated array. By summing the subarray 2, -1, 16, we get a total of 17, which is the maximum sum possible in this case. Therefore, the output is 17. This example highlights how strategically choosing the element to square can significantly impact the result. Now consider another example. If the input array is nums equals 1, -1, 1, 1, we can choose the element at index 1, which is -1, and replace it with its square, -1, caret 2 equals 1. This updates the array to 1, 1, 1, 1. The maximum subarray sum in this case is achieved by summing all the elements, which gives us 1 plus 1 plus 1 plus 1 equals 4. Hence, the output here is 4. For a third example, consider nums equals -2, -1, -3. In this case, squaring the element at index 1, which is -1, results in -1, caret 2 equals 1. The updated array becomes -2, 1, -3. The largest subarray sum here is simply 1, which is the result. These examples illustrate the importance of carefully selecting which element to square to maximize the subarray sum. Finally, let's discuss some edge cases to keep in mind. For a single element array, such as nums equals x, the result is straightforward: it's just x caret 2, since there's only one value to modify and consider. If the array contains all positive numbers, squaring the largest positive number increases its value, which helps maximize the subarray sum. On the other hand, if the array contains all negative numbers, squaring the least negative number, meaning the one closest to 0, produces the highest value, leading to the largest possible sum. Arrays with zeros also present an interesting scenario, as squaring a 0 has no effect, so the operation should target a different element. Lastly, for very large arrays with up to 100,000 elements, it's crucial that our solution is efficient and adheres to the given constraints. These edge cases highlight the variety of scenarios we need to handle in our implementation. To solve this problem, a brute force approach can be considered as a starting point. The idea is straightforward: for each index in the array, we replace the value at that index with its square, then compute the maximum subarray sum using Cadon's algorithm. After computing the sum, we restore the original value and move on to the next index. This ensures that every possible position is tested for the operation. However, the main drawback of this approach is its inefficiency. Since calculating the maximum subarray sum takes n time and we repeat this process for all n indices, the overall time complexity becomes n squared. This is feasible for small arrays, but it becomes impractical for larger ones. Additionally, recomputing the maximum subarray sum for every index introduces unnecessary redundancy, making this method less optimal for competitive programming scenarios. To address the inefficiency of the brute force method, we can use an optimized approach based on dynamic programming. The key insight here is to maintain two dynamic states for each index: the maximum subarray sum ending at that index without applying the operation, and the maximum sum where the operation has been applied to one element. We define these states as max_no_op and max_with_op. The transitions are straightforward. For max_no_op, we either take the current element alone or extend the previous subarray, whichever gives a higher sum. For max_with_op, we consider three possibilities: squaring the current element, adding the squared value to the best subarray without an operation, or extending the prior subarray where the operation was already applied. By iterating once through the array and updating these states dynamically, we can efficiently find the maximum subarray sum. This approach reduces the time complexity to O, n, and uses constant space, making it both scalable and efficient. Another way to optimize the problem is by using a sliding window approach with state tracking. This builds on Cadon's algorithm but avoids explicitly storing arrays for the two states, instead maintaining a single variable to track the effect of the operation. While this method retains the O, n, time complexity and further minimizes space usage, it can make the implementation more challenging to debug and understand. Ultimately, the optimized dynamic programming approach is chosen as the strategy for this problem. It strikes the right balance between performance and simplicity, ensuring an optimal solution while avoiding unnecessary complexity. By defining clear states and transitions, it also makes the solution intuitive to implement and easy to troubleshoot. This is especially valuable in competitive programming, where clarity and efficiency are equally important. When comparing the different approaches, the trade-offs become clear. The brute force method is conceptually simple but inefficient for large arrays due to its O, n squared, time complexity. Sliding window approaches that minimize space usage can further optimize performance but come at the cost of increased implementation complexity. The dynamic programming solution, on the other hand, balances efficiency with readability. It avoids redundant calculations while maintaining a clear structure, making it both fast and easy to debug. In conclusion, the dynamic programming approach is the best choice for this problem. It offers optimal performance with linear time complexity, handles large inputs effectively, and provides a straightforward implementation process. This combination of speed, clarity, and maintainability makes it the ideal solution for maximizing subarray sums after applying the operation. In this problem, we are tasked with finding the maximum subarray sum after modifying an integer array nums by squaring exactly one of its elements. The goal is to determine the maximum sum achievable. To tackle this, we start with a brute force approach. The intuition here is to modify the array1 index at a time by squaring the value at nums, I, then compute the maximum subarray sum for each modified array. To ensure we can process every index independently, we restore the original value of nums, I, after each computation. First, we initialize a variable max_sum to -infinity to track the highest subarray sum encountered. Then, we iterate over all indices in the array, squaring the value at each index while storing its original value in a temporary variable. This sets the foundation for the subsequent steps where we compute the maximum subarray sum for each configuration. After squaring the value at a given index, the next step is to compute the maximum subarray sum for the modified array using Cadon's algorithm. We initialize two variables, current_sum to 0 and current_max to -infinity. As we iterate through the array, we update current_sum by taking the maximum of the current element or the sum of current_sum and the current element. Simultaneously, we update current_max to track the highest subarray sum seen so far. Once the maximum subarray sum is computed for this configuration, we compare it with the global max_sum and update max_sum if the new result is higher. Finally, we restore the original value of the modified element before moving to the next index. Once all indices have been processed, the value in max_sum represents the maximum subarray sum achievable, and we return it as the result. There are a few key insights that make this approach efficient and straightforward. First, Cadon's algorithm is central to this solution, as it allows us to compute the maximum subarray sum in linear time for any given configuration. By leveraging this algorithm repeatedly, we can evaluate all possible configurations without introducing significant overhead. Additionally, modifying the array in place and restoring it afterward eliminates the need for extra memory to create copies, ensuring the space complexity remains optimal. While squaring each element and applying Cadon's algorithm for every index might seem repetitive, the efficiency of Cadon's algorithm makes this approach feasible, even for larger arrays. This iterative process ensures we evaluate all possible outcomes while keeping memory usage minimal. To implement this, we rely on the input array itself, a temporary variable for restoring values, and a few tracking variables such as max_sum, current_sum, and current_max. Breaking the solution into its key operations helps us understand the process clearly. The first operation is squaring the element at a given index, which introduces a potential new peak in the subarray sum by transforming negative values into positive ones or amplifying positive values. The second operation is applying Cadon's algorithm, which efficiently computes the maximum subarray sum in linear time for the modified array. Finally, restoring the original value ensures that other iterations use the unmodified array, maintaining correctness across all computations. When analyzing the complexity, the time complexity is O(n²), because we iterate through all indices, and for each index, we run Cadon's algorithm in O(n). The space complexity is O(1), as we only use a few variables for tracking and do not require additional data structures. This ensures the algorithm is efficient in terms of memory usage. It's important to consider edge cases to ensure the algorithm works correctly in all scenarios. For a single element array, the result will simply be the square of that one element since there are no other subarray sums to compare. When all elements in the array are negative, squaring any element will turn it positive, potentially yielding the maximum sum. With a mix of positive and negative elements, careful selection of which element to square becomes crucial to maximize the subarray sum. If the array contains 0, squaring it will have no effect, so it does not interfere with the computation. By addressing these cases, we ensure the algorithm handles a wide range of inputs effectively and robustly. The provided solution efficiently computes the maximum subarray sum that can be achieved by squaring exactly one element in the input array. Here's a step-by-step breakdown. 1. Initialization. Max_no_op tracks the maximum subarray sum without any squared operation applied. It starts as the first element. Max_with_op tracks the maximum subarray sum where one squared operation has been applied. It starts as the square of the first element. Result keeps track of the global maximum result, initially set to max_with_op. 2. Iterating through the array. For each element in the array, starting from index 1, calculate number_squared as the square of the current element. Update max_with_op by considering three scenarios. Adding the squared element to the best subarray sum without any operation, max_no_op plus number_squared. Adding the current element to the best subarray sum with one operation, max_with_op plus nums, I. Starting a new subarray with the squared element, number_squared. Update max_no_op by considering two scenarios. Adding the current element to the best subarray sum without any operation, max_no_op plus nums, I. Starting a new subarray with the current element, nums, I. 3. Update the result. The result is updated to the maximum of itself and max_with_op after each iteration. 4. Return the result. After processing all elements, the result contains the maximum subarray sum achievable by squaring exactly one element. The algorithm runs in O(n) time because it processes each element in the array exactly once, and its space complexity is O(1) since it uses only a fixed amount of extra storage. This Java implementation mirrors the Python logic for solving LeetCode problem number 1746, maximum subarray sum after one operation. It utilizes two variables, max_no_op and max_with_op, to track the maximum subarray sums without and with one square operation, respectively. The key difference in Java is the explicit type declarations and the use of math.max for comparisons. The solution iterates through the array, updating these variables and calculating the global maximum result. To solve this problem, we start with initializing three variables. The first, max_no_op, is set to the first element of the array, which is 1. This represents the maximum subarray sum without performing any operation. Then, max_with_op is initialized to the square of the first element, which is also 1 squared, or 1. This represents the maximum subarray sum where one operation has been applied. Finally, the result variable is initialized to max_with_op, since that's the best result we have so far. Moving into the first iteration, where I is 1 and nums, 1 is -2, we calculate the square of -2, which is 4. We then update max_with_op by taking the maximum of 3 values, adding number_squared, 4, to max_no_op, adding nums, 1, -2, to the previous max_with_op, or just number_squared by itself. This gives us a new value of 5. Next, we update max_no_op to the maximum of adding nums, 1, to the previous max_no_op, or just nums, 1, by itself. This becomes -1. Finally, we update the result to the maximum of the current result and the new max_with_op, which gives us a value of 5. In the second iteration, where I is 2 and nums, 2, is 3, we start by squaring 3 to get 9. Then, we calculate max_with_op as the maximum of 3 values, adding number_squared, 9, to max_no_op, -1, adding nums, 2, 3, to the previous max_with_op, 5, or just number_squared, 9. This results in a new max_with_op of 12. Next, we update max_no_op to the maximum of either adding nums, 2, to the previous max_no_op, or just nums, 2, which becomes 3. The result is then updated to the maximum of the current result, 5, and the new max_with_op, giving a value of 12. Now onto the third iteration, where I is 3 and nums, 3, is -1. Squaring -1 gives us 1. We then update max_with_op by taking the maximum of adding number_squared, 1, to max_no_op, 3, adding nums, 3, -1, to the previous max_with_op, 12, or just number_squared, 1. This keeps max_with_op at 12. The max_no_op is updated to the maximum of adding nums, 3, to the previous max_no_op, or just nums, 3, resulting in a value of 2. Finally, result remains unchanged at 12, as it is already the maximum value. In the fourth and final iteration for this example, where I is 4 and nums, 4, is 2, we start by squaring 2 to get 4. Next, we update max_with_op by taking the maximum of adding number_squared, 4, to max_no_op, 2, adding nums, 4, 2, to the previous max_with_op, 12, or just number_squared, 4. This results in a new max_with_op of 14. We then update max_no_op to the maximum of either adding nums, 4, to the previous max_no_op, or just nums, 4, which becomes 4. The result is updated to the maximum of the current result, 12, and the new max_with_op, which gives a final value of 14. This concludes the first example, where the output is 14. Next, let's analyze an example with all negative numbers. In this example, the input array is -3, -1, -2. We initialize max_no_op to the first element, which is -3. Then, max_with_op is set to the square of the first element, which is 9, and result is also initialized to 9. In the first iteration, where I is 1 and nums, 1, is -1, we square -1 to get 1. We update max_with_op to the maximum of adding number_squared, 1, to max_no_op, -3, adding nums, 1, -1, to the previous max_with_op, 9, or just number_squared, 1. This gives a max_with_op of 8. The max_no_op is updated to the maximum of adding nums, 1, to the previous max_no_op, or just nums, 1, which becomes -1. The result remains 9, as it is already the maximum value. In the second iteration, where I is 2 and nums, 2, is -2, we square -2 to get 4. We update max_with_op to the maximum of adding number_squared, 4, to max_no_op, -1, adding nums, 2, -2, to the previous max_with_op, 8, or just number_squared, 4. This keeps max_with_op at 8. The max_no_op is updated to the maximum of adding nums 2 to the previous max_no_op, or just nums 2, which becomes -2. The result remains 9, which is the final output for this example. Finally, let's consider an example with a single element in the input array, nums equals 5. Here, we initialize max_no_op to the first element, which is 5. Then, max_with_op is set to the square of the first element, which is 25. The result is also initialized to 25. Since there is only one element in the array, no iterations are needed. The result remains 25, which is the output of this example. This demonstrates how the algorithm handles the simplest case with a single element. Here, we analyze the time complexity of our solution, which is O(n), where n is the length of the input array. To break this down, the initialization of variables like max_no_op, max_with_op, and result takes constant time, or O(1). Then, we use a single loop to iterate over the array, which runs n times, contributing O(n) to the time complexity. Within each iteration, we perform several operations, such as squaring a number, updating variables using the max function, and calculating running totals. Each of these operations is executed in O(1) time. Since the loop runs n times and each iteration involves only O(1) work, the total time complexity sums up to O(n). This linear time complexity is a key advantage of this optimized approach. Now, let's consider the space complexity of the solution, which is O(1). The algorithm uses a fixed number of auxiliary variables, such as max_no_op, max_with_op, result, and number_squared, all of which occupy constant space. Importantly, we do not create any additional data structures or modify the input array nums. The computation relies entirely on these auxiliary variables without needing space that grows with the size of the input. This means that, regardless of the length of the array, the space usage remains constant. By avoiding additional allocations, the algorithm achieves an overall space complexity of O(1), which is highly efficient. To better appreciate the efficiency of our optimized approach, let's compare it to a brute force solution. In a naive approach, we would square each element of the array one by one and compute the maximum subarray sum for each modified version of the array. This would require iterating over the array repeatedly, resulting in a time complexity of O(n) squared, due to the nested loops. Additionally, storing each modified array could increase the space complexity to O(n), as extra memory would be needed to hold intermediate results. Clearly, this brute force method is far less efficient, both in terms of time and space. The optimized solution drastically improves on the brute force approach in both time and space. By using a single pass through the array, the maximum subarray sum is calculated dynamically, avoiding the need to compute subarray sums for every squared element. This reduces the time complexity from O(n) squared to O(n). Furthermore, since we only use a constant amount of auxiliary space, the space complexity is reduced from O(n) to O(1). The key insight here is leveraging dynamic programming principles to maintain running totals such as max_no_op and max_with_op, which allow us to efficiently update the global result. These optimizations mean that the algorithm performs consistently in the best, average, and worst cases, always processing the array in O(n) time and using O(1) space, regardless of the input values. Finally, we can mathematically confirm the algorithm's big O complexities. The total work performed is directly proportional to the number of elements in the array, n, as there are no nested iterations or recursive calls. This establishes the time complexity as O(n), reflecting the linear relationship between input size and processing time. Similarly, the space complexity remains O(1), because the algorithm does not allocate any additional memory that depends on the size of the input. All computations are performed using a fixed number of variables. These characteristics clearly demonstrate the algorithm's efficiency in both time and space. When tackling this problem, there are a few common mistakes to watch out for. First, if you're using a brute force approach that modifies the array, such as squaring an element, you must ensure the array is restored to its original state after each iteration. Failing to do so can lead to corrupted calculations in subsequent steps. Another issue is inefficiently recomputing subarray sums during brute force. Redundant calculations can slow down your solution significantly, so consider using optimized techniques like Cadon's algorithm or prefix sums. Additionally, edge cases are often overlooked. For example, you need to handle arrays with all negative numbers, arrays with just one element, or scenarios where the maximum subarray sum involves no modifications at all. Lastly, be cautious about integer overflow, especially in languages like C++ or Java, where squaring large integers can exceed the data type limits. Using the correct data types or applying modulo operations can help manage these cases effectively. Another mistake to avoid is misunderstanding the replace exactly one element constraint. Some solutions mistakenly square multiple elements or skip the operation entirely, which violates the problem requirements. Now, when it comes to interview settings, it's helpful to recognize key patterns. Problems that ask you to modify one element to maximize or minimize a result often require exploring all possible modifications. While brute force is a good starting point, leveraging greedy approaches like Cadon's algorithm can reduce time complexity, especially for maximum subarray problems. To optimize further, think about avoiding redundant calculations. For instance, pre-computing prefix sums can make your solution more efficient. Breaking the problem into smaller subproblems, such as finding the maximum subarray sum before and after modifying an element, can also simplify your approach and improve performance. In interviews, it's important to communicate your thought process effectively. Start by clearly explaining your brute force approach, even if it's not optimal. Then highlight its inefficiencies and explain how you plan to optimize it. This demonstrates a structured and thoughtful approach to problem solving. To deepen your understanding, you can explore related problems. For example, LeetCode 53, the maximum subarray problem, is a classic application of Cadon's algorithm. LeetCode 713, subarray product less than k, focuses on dynamically managing subarray constraints. Maximum product subarray, LeetCode 152, requires handling products and negative numbers, which adds complexity similar to this problem. Another related problem is LeetCode 1299, replace elements with greatest element on right side, which involves modifying array elements under specific constraints. These problems share conceptual similarities and can help you build a stronger foundation. There are also alternative approaches worth considering. For instance, a sliding window variation can help you dynamically track the current subarray sum without recomputing it from scratch. This reduces redundant calculations, though implementing sliding window techniques may be more challenging when modifications are involved. Another option is a divide and conquer strategy, which recursively finds the maximum subarray sum while modifying one element in each partition. However, this approach typically involves higher space complexity compared to Cadon's algorithm. Finally, you can pre-compute results by calculating the maximum subarray sums for all possible modified arrays. While this simplifies the main logic, it comes at the cost of increased pre-processing time and space usage. Each of these methods has trade-offs, so you'll need to evaluate which approach best fits the constraints of the problem and your optimization goals. Great job following along. In this session, we tackled the maximum subarray sum after one operation problem, breaking it down into manageable steps and exploring effective solutions. Remember to practice similar problems to strengthen your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!